Okay, so let's see this GATE 2002 question. What will be the answer for this? The minimum number of colors required to color the vertices of a cycle of n nodes such that two adjacent nodes no two adjacent nodes have same color. So this is your coloring problem. No two adjacent nodes should have same color. This is your vertex coloring problem. Okay, and you have a cycle of basically Cn. For Cn, you know the answer. The answer will be 2 if n is even. The answer will be 3 if n is odd. So which option is correct? Definitely this option is not correct, not correct, not correct. So the answer will be what? The answer will be option D. Actually, this is a beautiful question because if you notice this value, this will become 3 for n equal to odd. This will become 2 for n equal to even. If you notice this, n minus, if you notice this is your expression. Let's call it this expression E. So this is your n minus 2, n by 2, okay, plus 2. So this, if you notice that this, what will happen here? If n is even, then what will happen? For example, if n is even, like if you take n equal to 6, then what will happen? If n is even, then what will happen? Then you will get 2. And if you have n equal to odd, for example, let's assume 7. If you have n equal to odd, 7 if you take, then what you will get? Then you will get it 3. So this value, remember this value becomes 3. This becomes 2 when n is even, and this becomes 3 when n is odd. So this is your answer. Answer will be option D. Can you notice from this question, can you observe one thing about GATE exam? Please make one observation about GATE exam. GATE exam is basically all about these things. See, this thing is known to many people. Many people know this thing. But here, if they give nice options, like instead of these options, they should give nice options. Like this type of options they should give. This type of options they can give. Yes or no? This type of complicated options they can give. So this is what I'm saying. So this is the beauty of GATE exam. In the GATE exam, you have to apply your brain. If you by heart this, it will not help you, because another option can be, for example, they can change the option. And another option will be like this: 2, okay, n by 2 seal plus 2. Another option will be something else. Another option will be something else. So you have to find out. So the answer will be this, option D. Let's see this question. Okay, so tell me, from where to start for this graph? From where to start? There is, do we have K4? Do we have K4 in this graph? No, we don't have K4. There is no K4, but we have a triangle. But we have this triangle C3. Okay, so let's start with this C3. So I can start like this: 1, 2, 3. Okay, very simple. 1, 2, 3. 1, 2, 3. Okay, now what? Now what? Okay, so now you can reuse the color. This color number 1 you can reuse. Okay, this color number 1 you can reuse. Actually, what you can do, you can use color number 3 here, color number 1 here, color number 2 here. This is what you can do. Okay, and then whatever I do, I need color number 4 here, then I can use color number 4 here. So I have a 4 colorable. So I have 4 coloring. I know 4 colorable I have, but can I do better than this? Can I do better than this? I have 4 colorable, but can we do better than this? See, you cannot do better than this. You cannot do better than this, because notice what will happen. See what will happen. See, here you will give 2 different, here you will give 3 different colors. Now, if I do, for example, if I give color number 3 here, now I can give color number 1 here, I can give color number 2 here. Now notice here I cannot give color number 1, 2, 3. Now again I have to use color number 4, and then I can use color number 1. Then I can use color number, I have to use color number 4. And now which color I can use here? Okay, actually this, like this if I do, then I will get 5 colorable. Like this if I do, I will get 5 colorable. But ask yourself, can you do better? If I do like this, so it means chromatic number is less than equal to 5. Can we do using 4 colors? Yes, we can do using 4 colors. You can check it. This is the best you can do. You cannot do better than this. Okay, so actually cannot do better. Actually for this question, you have to try, you have to check, see, if you get the answer 5, then you try. For example, you get the answer 5. Let's assume you get the answer 5. Then you do better. Then you ask, can you do better? Can you do better? Okay, so this is what you ask. Can you do better? Now you can notice that, yes, you can do better. But now, can you again do better? Can you again do better? Actually, you can try. Okay, you can try in some 2-3 ways. You can try, and you will see that you cannot do better. You can try. Okay, basically you can try, but okay, cannot do better. Okay, so finally I can say the chromatic number will be 4 for this question. Okay, so you have to try. Basically for this question you have to try. Let's see this question. This is your GATE 2006. What is the answer? So the question is saying that there is a graph, and in the graph vertices are bit strings of length n. The vertices, they are the bit strings of length n, bit strings of length n. We have edge between two vertices if and only if they differ in exactly 1 bit position. They differ in exactly 1 bit position, So what is your graph G? Can you notice? What is your graph G? This is your hypercube graph. Yes, the definition of hypercube graph is given to you. This is GATE exam. This is GATE exam. See, let me tell you why this question is important. See, many people, they by heart notes. Okay, there are many people you will find what they will do. They will take some notes and they will by heart those notes. In those notes, it will be written. What will be written? In those notes, it will be written that Qn, okay, facts of Qn will be written. All the facts. You will see many people teach like this. Yes or no? Many people, what they will do? They will write facts, back to back facts. There will be 10 facts. Okay, and these facts you will by heart. If you by heart these facts, okay, then you cannot solve this question. First, you have to understand what is this Qn, that this graph is Qn. Okay, so never do this. Anyway, so let's come back to this question. So this is your graph G, and this G is basically your hypercube graph on. This is your hypercube graph Qn, because in hypercube graph we have strings of length n. How many vertices? Can anyone tell me how many vertices? There will be 2 power n vertices. You already know this. Now tell me, in the question, the ratio of chromatic number and diameter. What is the chromatic number of Qn? The chromatic number is 2. And what is the diameter? We have already seen diameter. Diameter is n. So the answer will be 2 divided by n. What will be the diameter? From this edge, from this to this, the path length, the distance will be 3. The distance will be 3. So this was the diameter. So the answer will be what? So chromatic number to diameter, the answer will be 2 divided by n. Is it clear? So like this. This is another question, GATE exam question. So what is the answer for this? What is the chromatic number of the following graph? For this graph. In this graph, do you have odd cycle? Do we have odd cycle in this graph? Yes, there is an odd cycle. See, this is the odd cycle. This is the C5. This is the C5. You got your C5. So you can notice this is your C5. These 5 vertices are giving you C5. So this is giving you C5. And so because it is C5, so what can you say about chromatic number? At least 3 you need. This is C5, right? A, B, C, D, E, A. A, B, C, D, E, A. Okay, this is your C5. A, B, C, D, E, A. So finally, what I can say, the chromatic number is at least 3. So give 3 colors. Okay, so let's start with this. Let's give 3 colors. Color number 1, color number 2, color number 1, color number 2, color number 3. I cannot give color number 1 here. Can I give color number 1 here? Can I give this? No, because these are adjacent. Okay, so I cannot give color number 1, color number 3. Now, can I reuse the colors? Can I reuse? Yes, color number 2 I can use. Yes, color number 1 I can use. Here, yes, color number 1 I can use. And what about this point? So I can use color number 2. Okay, so the answer will be 3. And okay, so this is 3 colorable. So we got 3 colorable. Can I guarantee at least? Okay, can I guarantee 3 colorable means chromatic number is less than equal to 3? Okay, and this is saying chromatic number is greater than equal to 3. So finally, I can say chromatic number will be 3. I can guarantee 3. Okay. This is another question, GATE exam, GATE 2009. What is the answer for this question? The chromatic number of a n vertex simple connected graph. N is greater than equal to n is greater than 2. N vertex simple connected graph, which does not contain any odd length cycle. It means your graph is what? It means your graph is what? Your graph is bipartite. Your graph is bipartite. For bipartite, what should be the answer? For bipartite, what should be the answer? The answer should be at most 2. The answer should be at most 2. The answer should be at most 2. But why the answer is exactly 2? Here the answer will be exactly 2. Why? Because n is greater than equal to 2. Okay, remember, n is greater than 2 and connected. These words are very important. Okay, connected and greater than 2. Okay, so these two things means at least one is. These two things means at least one is. We have at least one is. So that is the reason chromatic number will be greater than equal to 2. So chromatic number will be greater than equal to 2, less than equal to 2. So finally, I can say chromatic number will be 2. Why this is bipartite? Because there is no odd cycle. A graph is bipartite if and only if there is no odd cycle. Bani, a graph is bipartite. We have already seen this is important theorem. A graph is bipartite if and only if no odd length cycle. Another statement, the graph is bipartite if and only if every cycle has even length. The same statement I can write like this. A graph is bipartite if and only if every cycle has even length. Every cycle has even length. Okay, every cycle has even length. So this is the idea. So this graph is bipartite, and you can notice that because it is connected and n is greater than equal to n is greater than 2, so there is at least one edge. So that is the reason I can say chromatic number will be 2. Okay. In this same question, if I remove this, and if I say n is greater than, if I say n is greater than equal to 1, then remember the answer will be at most 2. Then for this question, and if options are like this, let's assume options are like this. Let us assume options are like this. Then the answer will be option B. Because you know, if you have n equal to 1, then the chromatic number will be simply 1. Okay, so this is the idea. And this is the GATE exam question. This we have already seen. So I told you that for this question, what will be the answer? What will you do? You will start with the cycle. What will you do? You will start with the C3. This C3 I can see 1, 2, 3. But what you do after this? If you take this, because I can reuse this color number 2. After this, if you take this, okay, and you can use color number 3 here, and you can use color number 1 here. So now we have a 3 colorable. Now what we have? We have 3 colorable. It means chromatic number is what? Less than equal to 3. Can we do better? Can we do better? No, there is a cycle. There is C3 here. So there is C3 here, and this C3 means you need at least 3 colors. Okay, so these 2 points means the chromatic number will be 3. So we have seen all the questions, everything we have seen. For this question, what will be the answer? So color the vertices with as few colors as possible. Okay, minimum number of colors you need. So what should be the answer for this question? So again, there is a cycle. You can see there is a cycle. So you can start 1, 2, 3. You can start with 1, 2, 3. Then what you can do? Then you can reuse color number 2 here. You can reuse color number 3 here. You can reuse color number 1 here. So the chromatic number here will be 3. Okay. You can guarantee 3 because there is a cycle. Because there is a C3, so you can guarantee that the chromatic number will be greater than equal to 3. You can guarantee. And because we got 3 colorable, the graph we got is 3 colorable. It means the chromatic number is less than equal to 3. So finally, I can say the chromatic number will be 4. Okay, so from these two, from this and from this, I can say the chromatic number will be 3. So you can notice this is the definition of chromatic number. Chromatic number is the minimum number of colors needed. Okay, and you already know that if G is K colorable, then chromatic number will be less than equal to K. If G is K chromatic means chromatic number is K. K chromatic means chromatic number is K. K colorable means chromatic number is at most K. So this is the idea. Okay. So all the things we have seen, this thing we have seen, if G is a graph, then chromatic number will definitely be what? Greater than equal to clique number. So this equation we have, that chromatic number will be between clique number and this maximum degree plus 1. So between that. One last thing, actually, one very interesting thing we need to see. What can you say about if, okay, this is my question. Okay, let's assume you have a graph G. Let us assume you have a graph G and this is properly colored. Let's assume this is properly colored. Then a particular, okay, then vertices of a particular color, what they will create? This is properly colored. Then vertices of a vertices, all vertices of a particular. So vertices of a particular color, what they will create? Okay, forms. What they create? What they create? They will create independent set. Very good, because they are non-adjacent of a particular color. Like particular color, for example, red color. So if you are giving red color, it means what? It means they are independent set. They don't have any edge. Because you are giving red color, it means what? It means what? If you are giving red color, it means what? They are non-adjacent. They are pairwise non-adjacent. So they are independent set. So they will create independent set. Very simple. So remember, if you notice the color classes, what are the color classes? What are the color classes? What is that? Color classes means like this. What you do? You have a graph G. Okay, color classes means what you do. So these vertices you can divide into color, like color classes. Like, okay, all the vertices of red color here. Okay, all the vertices of green color here. All the vertices of green color here. All the vertices of blue color here. Okay, and so on. And so on. So you can notice this is called color classes. What you can do? All the red color vertices are here. All the red color vertices. All the green color vertices here. All the blue color vertices here. Now tell me one thing. Is it possible that they have edge? Is it possible there is any edge? Is it possible there is any edge? The answer is no. The answer is no. Is it possible there is any edge? The answer is no. Is it possible there is any edge here? There is any edge here? Again, the answer is no. So this color class, if you notice, this will be an independent set. This will be an independent set. This will be an independent set. Okay, because this is the idea. Is it possible that there is edge here? Is it possible there is edge like this? Yes, this is possible. This is possible. There is no problem. These things are possible. These things are possible. These things are possible. So this is the idea. Okay, color classes. Now, very important point. Okay, few interesting things we will see. This is the question. If G has chromatic number Okay, if G has chromatic number, if G has chromatic number K, if G has chromatic number equal to, let's assume M. Okay, if this is your chromatic number, then my question is, what can you say about number of edges? Then can I say number of edges will definitely be greater than equal to MC2? This is my question. Prove. Okay, then prove that number of edges will be, number of edges in G, number of edges in G, that will be greater than or equal to NC2. Let me tell you why. What is the reason? Let me tell you. See, very simple. The point is actually very simple. Just tell me this point. Chromatic number means what? Chromatic number is M. It means what? It means this is the minimum number of colors needed. It means this is the minimum number of colors needed. Yes or no? Number of colors needed means you cannot do better than this. Agree? Okay, agree. This is the idea. Chromatic number means minimum number of colors needed. So let's assume that these are your color classes. Let's assume your color classes like this. Okay, so for example, let's assume this chromatic number is 4. Let's assume. So let's assume your chromatic the color classes are like this. You have a red color here, you have green color here, and you have blue color here, and you have black color here. So let's assume this is the idea. Now tell me one thing. I'm asking, no, I'm asking Nikhil, I am asking that at least these many edges will be there. Minimum number of edges, how many will be there? Minimum means this is the minimum number of edges. What it means? It means minimum number of edges. It means minimum number of edges in G. Remember this. It means minimum number of edges in G. Minimum number of edges in G is MC2. This is the minimum number of edges in G. But how to do this? Like minimum, how many edges you need? See, there is no edge here. 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 Is it possible you don't have any edge? Tell me one thing. Is it possible you don't have any edge? Is it possible there is no edge? Just tell me. Is it possible there is no edge? Is it possible there is no edge? Why? What will happen if there is no edge? If there is no edge, then what will be the contradiction? The contradiction will be this. This will be the contradiction. Because chromatic number is 4. If chromatic number is 4 means this is the minimum number of colors needed. So if you don't have any edge, let's assume there is no edge. Let's assume there is no edge. Then the chromatic number should be 1. Okay. So there is a contradiction. If you don't have any edge, there is a contradiction. I can say if you don't have any edge, then there is a contradiction. If you don't have any edge, no edge implies contradiction. Okay, so there is no, okay, that is a contradiction. What will be the contradiction? The contradiction will be that zeta will be 1, but already zeta is 4. Okay, so there is a contradiction. Another thing, tell me another thing. Is it possible there is no edge between them? Is it possible there is no edge between these two? Is it possible there is no edge between these two? Between these two there is no edge. Like between these two there is no edge. Is it possible between these two there is no edge? If there is no edge, then what is the problem? If there is no edge, what is the problem? Tell me the problem. If there is no edge between them, then you will merge. Then merge them. Then merge them. Then merge them. And the chromatic number will be what? The chromatic number will become 3, but chromatic number is 4. So again there is a contradiction. So again there is a contradiction. So then merge them. Okay, but okay, so this but is giving you contradiction. This is giving you contradiction. So what it means? It means, so final conclusion. Now tell me the final conclusion. The final conclusion is there is at least one edge between every color class. There should be at least one edge between every color class. This is the final conclusion. At least one edge should be there. At least one edge should be there between every color class. Between every color class, At least one edge should be there. At least one edge. So minimum number of edges I am asking. I am asking minimum number of edges between every color class. At least one edge should be there. Agree or not? So between every color class, okay, remember, between every color class, at least one edge must be there. At least one edge must be there. Okay, between every color class in a minimum coloring. Okay, between every color class in minimum coloring. In minimum coloring. If your coloring is minimum, then this would happen. Remember, if your coloring is not minimum, then this will not happen. See, if your coloring is minimum, A, B, C, D, if your coloring is minimum, like red, okay, like if you have this coloring, green, so here your coloring is minimum. This is a minimum coloring, correct? This is a minimum coloring. And because this is a minimum coloring, so you can notice these are the red vertices, A, D. These are the red vertices. And these are the green vertices, B, C. And you can notice, because this is the minimum coloring, so there is at least one edge. This is independent set. This is independent set. And there is at least one edge. There is at least one edge. I can say there is at least one edge. You have at least one edge. Okay, there can be more than one, but there is at least one edge. Okay, so this is the idea. At least one edge is there. But remember, if you don't do minimum coloring, then this is not guaranteed. If you don't do minimum coloring, for example, color number 1 here, color number 2 here, color number 3 here, color number 4 here, then color number 1, who are the color, like, okay, maybe red, let me give some other color, like, okay, red color here, green color here, blue color here, and some other, I'm forgetting colors, yellow, okay, yellow color here. So you can notice here now red color is this, the green color is this is the color class, the blue color class is this, and the yellow color class is this. Now there is no guarantee, yes or no. Now this is not minimum coloring. This is not minimum coloring. Now you can notice there is no edge between these two. For example, there is no edge. You can notice there is no edge. So are you getting my point? So if you have between every color class, in a minimum coloring, this is important, in a minimum coloring, okay, at least one must be there between every. So what can I say about number of edges? At least how many edges must be there? At least how many edges must be there? So chromatic number C2. Yes or no? Between every two there should be. Okay, so there are how many color classes are there? How many color classes? These many color classes. These many color classes you have. Chromatic number. This chromatic number is equal to the number of color classes. So the number of color classes will be zeta. And between every two color classes, you must have at least one edge. Between every two of them. So, okay, so minimum these many colors will be, minimum these many edges will be there. Is this clear? Let me know. Is this clear to everyone? How many of you got it? Did you understand this? Let me know. Please let me know if you have doubt. Do you have doubt? Any doubt in this? Okay. So very simple. Now, maximum how many edges can be there? This is the next question. If your graph is like this, okay, then what is the maximum how many edges can be there? Your graph is this, and let's assume this has chromatic number is this. This zeta is the chromatic number. Okay, this is your chromatic number. If this is your chromatic number, then what is the maximum number of edges you can have? Maximum number of edges. What is the maximum number of edges? Very simple. Maximum number of edges. This is actually very simple. because these are, let's assume these are your color classes. Your color classes are these. For example, red, these are the red, okay, and these are the green, okay, and so on, okay, and so on. So, okay, you can notice one thing, that if your chromatic number is this, if your chromatic number is this, then maximum how many edges you can get? Maximum how many edges you can get? So to get maximum, what you will do? See, to get maximum, you can notice if there are some vertices here, then they are independent set, right? They are independent set. They are independent set. Okay, so for every color class, any color class you take, any color class you take, that does not have any edge. There is no edge here. There is no edge here because these are the red, so there is no edge here. Similarly, this is independent set, so there is no edge here. So if you want maximum number of edges, then what you will do? Between every vertex of this and every vertex of this, there will be edges. Okay, this is what you will do. This is what you will create. This is what you will create. Okay, you will create like this. This type of situation you will create, right? Okay, right, like this. This type of situation you will create. Agree? Do you agree? Okay, so basically, actually, we cannot find because we need the data. We need how many vertices are here, how many vertices are here, how many vertices are here. This data we need. But I am saying that to get maximum, this is what you can do. For example, okay, let's assume that you have a graph G, and in this graph G, let's assume there are 20 vertices. Let's assume there are 20 vertices, and let's assume this for this graph, the chromatic number is 4. And these are the 4 color classes. You have total 4 color classes red. In this color class, let's assume there are 5 vertices. Okay, and there is yellow. In this color class, let's assume there are 4 vertices. And there is green. In this color class, let's assume there are 2 vertices. And there is blue. So how many are remaining? So let's assume there are 9 vertices. Okay, now tell me what is the maximum number of edges? So what is the maximum number of edges will be there? What is the maximum number of edges now? So very simple. So what you will do? Between every vertex of this and every vertex of this, there will be edge. Yes or no? Between every vertex of red and yellow, this is what you will do. For red comma yellow, what you can do? For every pair of vertices, you will create edge. You can take one vertex from here, one vertex from here, and you will create edge. So how many edges you can create? Tell me. So how many edges you can create? These many edges, these two will create. These many edges, these two will create, like red and yellow. Okay, similarly, this red and green, how many edges they will create? How many edges they will create? So you can notice between every 2 vertices here, you will create edge. So there will be 10 edges. There will be 10 edges like this. So finally answer will be what? So the final answer will be what? Let's see, because of red, you are getting, okay, if you notice, because of red, you are getting 5 into 4, 5 into 2, 5 into 9. So this is what you will get. 5 into 4 plus 5 into 2 plus 5 into 9. This you will get because of red ones. Next, because of yellow ones, what you will get? This yellow one is counted here. So because of the yellow ones, what you will get? You will get 4 into 2, 4 into 9. 4 into 2, 4 into 9. Okay, what is remaining? Green ones, 2 into 9. 2 into 9. So this will be your answer. You can add all of them. That will be your final answer. Is it clear to everyone? So remember, if I ask you maximum number of edges, then what you will do? Remember, this is independent set. This red is independent set. This yellow and this green is also independent set. So there is no edge. There is no edge between these 5 vertices. Between these 5 vertices, there is no edge. These 5 vertices, they are independent set. These 5 vertices are independent set. But between these color classes, you can make all the possible edges. All the possible edges you can make between these color classes. So this is the idea. So you can notice minimum how many edges will be there? These many. We have already seen. What is the logic? One line. In one line, what is the logic for this? What is the logic for this in one line? How many edges? Minimum how many edges will be there? That is chromatic number C2. That is chromatic number C2, and that is same as chromatic number into chromatic number -1 divided by 2. And what was the logic for this whole thing? What was the logic? The logic is between every color class, at least one edge must be there. At least one edge between every pair of color class. Very good. Yuvraj, very good. Excellent. Okay. So that's it. And this is also very easy. This is another very easy thing. Let's see the proof for this. This is actually very easy. So tell me one thing. If you have a graph, and let's assume in this graph, the chromatic number is this. This is the chromatic number. If this is the chromatic number, then what can you say about the largest? Okay, what can you say about size of? What can you say about size of largest color class? So what is the size of largest color class? Like size of average color class. Tell me. Average, like at least one color class you will have, right? Yes or no? Size of average color class. What that will be? Size of average color class. What that will be? You have these many color classes. So average color class size will be what? That will be number of vertices divided by zeta. Number of vertices divided by zeta. Because these are your color classes. Your color classes are like red, green, okay, blue, and so on. And so on. These are your color classes. Some vertices are here, some vertices are here, some vertices here, and so on. So size of average color class, like on average, what is the size of a color class? That will be this. Yes or no? On average. On average. Okay, so can I say there is at least one color class with these many vertices? Can I say there is at least one color class with these many vertices? Okay, so there is at least one color class. So there is at least one color class with, remember, there is at least one color class with how many? There is at least one color class with these many vertices, with this average number of vertices, right? With average number of vertices, with average number of vertices. Okay, with at least these many vertices, with at least average number of vertices. Is this clear? This is the meaning of average, right? If average is this value, if average value is, for example, if average value is k, what it means? It means there is at least one person less than equal to k. There is at least one person greater than equal to k. Yes or no? This is the meaning of average. That is the meaning of average. Like someone is small, someone is bigger, small, bigger, small, bigger. So the average meaning is this. So I can say that there is at least one color class. At least one color class will have at least these many edges, these many vertices. Okay, and this color class, this is an independent set. So what can you say about independent set? What can you say about independence number? This is independent set. You know, this is independent set. This is independent set. So what can you say about independence number? So finally, what can I say about independence number? That should be greater than equal to this. Independence number should be greater than equal to this. Isn't it? Because this is already independent set. See, this color class, this is already independent set. This color class is already independent set. And this color class has these many vertices. At least these many vertices. At least these many vertices are there. Okay, at least. Maybe more. Maybe more. More than this can be there. Okay, maybe more. At least these many vertices this color class has. This color class is independent set. So we have an independent set. We have an independent set with at least these many vertices. We have independent set. This independent set we have with at least these many vertices. So what can we say about independence number? So the largest independent set that will be greater than equal to this. So I can say alpha is greater than equal to number of vertices divided by zeta. And from this, what you got? If you simplify this, then what you will get? Then you will get alpha into zeta is then what you can say? Number of vertices is less than equal to alpha into zeta. The proof is clear. All these proofs, are they clear? See, these proofs are very easy. Okay, if you just apply the definitions, these proofs will improve your knowledge a lot of, like, whatever question comes in the GATE exam, whatever question, new question, any complicated question they give you, you can solve it. And these proofs are very easy, very basic things we are using. We are using the definitions, nothing else. Okay, is this clear? This proof is clear to how many people? So this is the idea. Okay, so these two things we have seen, and this is actually a TIFR question. Let me tell you, everything that we study that can come in the GATE exam, that can come in GATE exam or TIFR exam. See, this is the TIFR question. Now solve this question. Now solve this TIFR 2013 question. What this question is saying? There is a graph, undirected simple graph on n vertices. The definition of coloring is given. The coloring definition is given. Coloring is assignment of colors to each vertex such that end points of every edge have different colors. End points of every edge are different colors. Yes, correct. End points of different, if you have some edge, then end points must have different colors. They must have different colors. This is the definition of coloring. This zeta denotes the chromatic number, means the minimum number of colors needed in a valid coloring. This is the chromatic number. And this set B is given to you. This set B is independent set if no vertices are connected by an edge. This is the, okay. And this alpha is given to you. This is the size of largest possible independent set. Can you see this question is so well framed? Okay, like this type of questions, we love it. Like, okay, when you see this type of question, well framed, right? Every information you have, so you don't have any ambiguity. Every information is given. Chromatic number, coloring, independent set, okay, independence number, every information is given to you. There is no ambiguity. This is a very beautiful question. And this type of questions you will find in the test series also. GATEOverflow Go classes test series, the combined test series you can take. In that combined test series, you will see this type of well-framed questions. Every question, okay, like have you seen any test? Have you given any test? Every test has, well-framed question. There is no ambiguity in any question, right? You can check it out. Every question is well-framed. Okay, so you can basically, you should definitely attempt GATEOverflow and Go classes combined test series. You should definitely attempt this type of nice questions you will find. Okay, anyway. Okay, so tell me now, what can you say? So you have independence number. So what we can say, we know that n is, we know, so what we know that alpha is bigger than n divided by chromatic number. This we have already seen. Alpha is bigger than, okay, and what is this? This is the average size of color class. So, okay, so this is the average size of color class, and every color class is what? Every color class is independent set. So this is the average size of color class. And every color class is independent set. So the largest independent set should be greater than equal to this. The largest independent set that should be greater than equal to this. So the answer will be what? The answer will be option C. Is this clear? The answer will be option C. And this is another TIFR question. Tell me quickly, what is the answer? TIFR 2017. What should be the answer for this question? A vertex coloring of a graph with k colors a vertex coloring of a graph with k colors. So this definition is given. The definition of vertex coloring is given. If you notice, see, the definition is given. Vertex coloring, the definition is given for vertex coloring, that a vertex coloring with k colors, that is a mapping. Means you are mapping the vertices into the colors. What you are doing? You are mapping the vertices to colors such that. If you have A's, then they have different labels. If you have A's, then they have different labels. See, this is the definition of coloring from as a function. This coloring as a function, you can think of coloring. This coloring you can think as a function. This coloring you can think as a function. So what you are doing? Basically your vertices. These are your vertices. 1, 2, 3, and so on. These are your vertices, and these are your colors. These are your colors like red, okay, green, blue, and so on. So what you are doing? This coloring is basically to every vertex, how many color we give? To one vertex, how many color we give? Tell me. To one vertex, how many color you give? Only one. Okay. And to every vertex, do we give a color? To every vertex, do we give a color? Do we give a color? Yes. So this is a function, right? Yes or no? This is a function, because every vertex should have exactly one color. Every vertex should have exactly one color. Should have exactly one color. Every vertex should have exactly one color. So this is a function. This is a function. And what is the condition for this function? This is your coloring function, I can say. This is your coloring function f. And what this function has the condition? What is the condition on this function f? This function f, this is from v to colors. From v to colors. And what we have? You can notice that if u comma v belong to age, if u comma v belong to age, means if they have age, then what should happen? Then what should happen? Then fu should not be equal to fv, right? Yes or no? Then they should not get same color. fu should not be equal to fv. Agree? Yes or no? If two are adjacent, if they are adjacent, u comma v, if they are adjacent, then they should get different colors. If these two people are adjacent, then they should get different colors. So this is the definition of coloring as a function. Is this clear? Coloring as a function. Is this definition clear? That coloring is basically a function from vertices to colors. From vertices to colors. This is a function. Because every vertex should get exactly one color. To every vertex we give exactly one color. So this is a function. We cannot give like this, because every vertex should get exactly one color. And if you have some age between two vertices, then they should not get same color. They should get different color. Like if they have age 1, 2, then if they have age, let's assume if they have age, then they should not get same color. This should not happen. They should get different colors. So what is the answer for this question? Which statement is true? Which statement is true? Three statements are given to you. Every tree admits a vertex coloring using two colors. Remember, this question is not talking about chromatic number. The question is talking about basically vertex coloring, k colorable. This is the definition of k colorable. This is not the definition of chromatic number. This is the definition of k colorable. So remember, this is the definition of k colorable. Definition of k colorable as a function. As a function. Okay. So definition of k colorable as a function. And what is k? The size here, this is the size k. This is your size k. Means this has size k. Number of colors is basically k. How many colors you have? Total k colors you have. Then we will call it, this is k colorable. So then this will be called k colorable. Then we can say this f is k colorable. This f will be called k colorable, because this is your coloring function. So this is the definition of colorable. This is not the definition of chromatic number. So tell me, can I say every tree is two colorable? Can I say every tree is two colorable? A tree is a bipartite graph. Why tree is a bipartite graph? What is the reason? Why tree is a bipartite graph? Tree is a bipartite graph because there is no odd cycle. There is no cycle. There is no cycle, so there is no odd cycle. So yes, this is correct. What about this? Every cycle admits a vertex coloring of using two colors? No. Okay, what about this? If every vertex has degree at most k, at most d, then G admits a coloring of d plus 1 colors, d plus 1 colorable. This is correct. This is also correct. So the answer will be what? That will be 1,3. Okay. So this is your all the questions we have seen. All the questions, every TIFR, every gate question we have seen. I did not leave anything. Every question we have taken. So in this class, in this video, you have every question of gate exam, every question of TIFR exam on coloring. Did you understand? Did you understand all the concepts? And did you see the relationship? Did you understand the relationship? So these are the conclusions that we have seen. That chromatic number is basically greater than equal to click number, then that is click number, and that is less than equal to the maximum degree plus 1. This we have seen, the first thing that we have seen. Okay, and the second, can anyone tell me here who understood everything? Like if I want to take your viva, will you give, like if I ask you, do you remember why this happens? Do you remember why this happens? Will you be able to answer? Like for example, why this happens? Why this happens? Because this is a complete subgraph, so it should get different colors. It should get different colors. Why this happens? Why this happens? Because of greedy algorithm. Why this happens? Because of greedy algorithm. In worst case, you have to use from 1 to delta plus 1. Only these colors you have to use. Okay, and the next thing, yeah, minimum number of edges, that will be greater than equal to chromatic number C2. Okay, the same thing I can write like this. The minimum number of edges will be chromatic number into chromatic number minus 1 divided by 2. And the another thing is alpha. This is greater than equal to n divided by chromatic number. What is this? Anyone want to tell me what is this? This is the average size of color class. This is the average size of color class. And every color class is what? Every color class is an independent set. Every color class is an independent set. So the independence number should be greater than equal to this. Okay, so these are all the facts that we have seen. And that's it. So this is your coloring chapter, and this is enough for today. We will study this age coloring. We will study tomorrow. In the next class, we will study this age coloring. Okay. Graph theory is very important for GATE exam. For any exam, graph theory is important for your interview. By chance, if you prepare very nicely, and let's assume you get 600, 500 rank, then in the interview, they will ask you graph theory. Okay, so that is the reason we are learning this graph theory is in a very nice manner. Okay, so in this class, we have seen a lot of questions, all the GATE question, all the TIFR question, all the theorems, all the proof, every definition, every concept, every variation, every corner case we have covered. This is the complete package for coloring, vertex coloring. This is the complete package.